So today what we'll look at is we'll look at a bit more detail about this four-way handshake as part of the contention-based random access. I hope you have gone through the material that I already posted, but in case you have any doubts during today's class, we'll discuss those things again. So what you see here, I hope all of you are able to hear me. So could somebody confirm me?
Yes, sir. Sir, I have a question
Yeah,
regarding
last
earlier.
classmate. Is it?
Yes, yes.
Please start.
So I read somewhere that in case of LTE, the SIBs are always on, like always transmitted. But in case of 5G and on, only SIB1 is always transmitted, and the remaining SIBs like OSIs are transmitted when the someone is getting connected, like after the initial access, like after PSS, SS, PBCH connections are done. Then only the base station starts sending the SIB2, SIB3 to SIBN.
Right.
Okay, so I just want to
No,
confirm.
but that's what even I covered, right? Can you look at my screen?
Yes.
So in this slide, this is exactly what I was conveying. You look at, we have MIB and SIB1 has periodicity of 80 millisecond and 160 millisecond, which are transmitted all the time in a broadcast mode. Whereas other ones that you can see in this slide, SIBN, that is number like it could be 2, 3, 4, 5, 6, 7, 8, and 9. So can be transmitted in broadcast manner or in unicast manner, but only when there is a request coming from the user equipment side.
Okay, okay. So dash means on demand. Okay, fine.
Dash. Where do you see dash?
Like the arrows are solid arrows for the first two ones, and the rest of them are
Right.
dotted
Okay.
arrows.
But it is written, right? Unicast. Okay. Yeah, you can think of that. Yeah, you're right.
Okay. Okay, sir.
Any such queries related to these SIBs or MIBs? And also, I didn't tell you explicitly, but if you actually look at the initial or the first RRC messages, are these MIB and SIBs and SIB1 to be more precise, because they're always transmitted. So in the RRC layer, the first message that is transmitting in the network are the MIB and SIB1, which are transmitted in using this PBCH and also using downlink shared channel in the case of SIB1. After that, yeah, the connection setup request and registration messages and other things are transmitted, which also comes under RRC messages. So any other doubts related to, yeah.
So I had one question. So PCI is equal to 3 into NID1 plus NID2. So NID2 was physical layer identity, which could take values between 0 to 2, 0, 1 or 2. And this 0, 1 or 2 is unique for a cell. Right, sir?
Right. Okay.
So I wanted to ask, like, why do we need to have like 3 different kinds of this NID2? Like, only one could be sufficient.
I didn't get. What you are asking is why we need to have?
Like NID2, it can take 3 values, right? 0, 1, and 2.
Right.
And for one particular cell, only one NID is fixed.
Yes.
So why do we need to have other 2 kinds of NID2, or like why do we need to have like 3 variations? Only one would have been sufficient.
Yeah, see, if you look at it at the end of the day, any given cell will take one out of these 1008 PCIs.
Yeah.
But how a given cell, basically how a user who is planning to connect with a base station comes to know what is the PCI. For that, what we are doing is we are transmitting PSS and AAAS, where inside PSS we are transmitting NID2, which could be taking value either 0, 1 or 2, and AAAS we are transmitting NID1, which can be taking any of those 336 values. So by decoding these NID1 and 2, by substituting these two in this particular formula, a given user will come to know what is the cell identifier.
Okay, but sir, like if there would have been 1008 SSS, so
Mhm.
it had been a problem like without
No, we
this?
can have it. We can have it. What you said is absolutely correct. But thing is, in the case of LTE, we have similar structure where we have PSS and AAAs. We're using PSS. We can able to identify one of the three physical identity. Using AAAs, we can identify one out of. I think we have something like. It is 504. So we have to divide 504 with 3. It is 168, right?
Yes.
So what I'm trying to say is, in the case of LTE, so we had 504, okay? So that is achieved using 168 groups and 3 identities. So combination of these. So whatever that we have it in LTE has been extended into, like in this case, I'm talking about 336 and 3. So together we are getting 1008. So what you are saying also is possible. What you are saying is that I don't require PSS and AAAs. I will transmit PSS alone. So which can identify one out of 1008. That's what you are trying to say, right?
Yes, sir.
That is also possible. But in this case, what 3GP has done is they're trying to make sure you make minimal modifications as you go from 4G to 5G. Where in the case of 4G, as I was mentioning, we have um, AAAs and also PSS. So the way it is transmitted in LTE, this is the time and in frequency. So in the center 6 RBs. So these AAAs and PSS are transmitted to identify 3 and this 168 different things. So they kind of retain the same thing. And one problem that you also get when you're trying to identify, like if you come back here, so you are saying that by sending one signal, you wanted to identify one out of these 1008, right? And also, if you recall, I was talking about in the previous class, when it is coming in the case of this. So we have 336 code sequences. It is Anvesha, right? Who is asking this question?
Yes, sir.
Okay, my question to you is, and here we have 3 code sequences. So my question to you is, when you are transmitting, let's say, this is in PSS and this is in AAAs. So when you're transmitting, let's say PSS, using 3 different code sequences, where you wanted to identify one out of these 0, 1, and 2. So that is what you are trying to do that. So I was mentioning that we use a longer code sequence.
Yes, 127 bits
So it
of
is one,
M sequences.
yes, we are using a bit length of 120 bits, which are modulated using BPSK into 127 symbols and transmitting. But as you try to make one signal to we identify these 1008 different identities, what could happen? So we need to have at least 1008 code sequences, right?
Yes.
And in this case, how many we have in like in the case of 5G? So if we come back here, we have 127 subcarriers we are using for transmitting PSS, right?
Yes.
and we have 127 bits available. So using which you wanted to realize 1008 different code sequences. It is possible to do that, but compared to the case where you wanted to have 1008 code sequences, when you are having, let's say, 336 code sequences to represent different things, so the probability of you able to the probability of you are able to distinctly identify these code sequences will be higher as the number of code sequences are distinct apart from each other.
Yes, yes.
So that way, as you try to put more and more code sequences within a given bit pattern, so there could be a chance that when due to because of the bit errors, you may treat one code sequence as something else because there is no CRC or anything as part of these basic reference signals, and there is a slight chance that things may go bad. So for that, what they have done is let's not to pack too many code sequences inside a given 127 subcarrier that you have out there.
Yes, got it, sir.
And see, also one can simply transmit log 2 base 336 bits alone. Directly you can transmit these many bits. But we are not doing, right? We are actually transmitting 127 bits. Basically with a lot of redundancy and other things using these code sequences. I'm talking about like length M code sequence where the length here it is 127 bits. Okay, so any other doubts anyone having?
Yes, sir.
Sir, I
In
have a query.
Ah,
Sir, I
so,
have a query.
okay, Ranjita, continue.
yeah, one of you go ahead.
Yeah, sorry. Sir, I have a query regarding the IMSI and MS ISDN mapping.
Okay,
So
okay.
we
I think
can,
just hold on. The other question is also related to this, Suranjan, or something else? Yeah, if that
No,
is the
it is related to SS burst.
okay, okay. So first we'll complete this, then we'll look at IMSI and IMEA and other things. Okay, go ahead quickly.
Sir, in MS burst, the size is always 5 milliseconds, right?
Okay, so maybe I will go back to the presentation. Yes,
So it is always 5 milliseconds, but the number of SS blocks can be 4, 8, or 64.
right, right.
So if we are packing more and more SS blocks, how are we like doing it? Like in the time domain, the time is constant, but we are increasing
But time
its
is constant, but as you go to higher numerologies, what you are getting more?
frequencies. Okay.
No, 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 no. Higher numerologies. For a given bandwidth, as you go from lower numerologies to higher numerologies, what is the thing that you are gaining additionally in time domain?
Yeah, yeah. This SC, the subcarriers.
No, no, no. Time domain. Again, you are confusing. I'm asking in time domain. Can somebody else answer this part?
number
One
of
slots.
So this is 1 millisecond subframe. Okay. So if you look at different numerologies, oops, what is it? Okay. And for subframe 0, 1, 2, 3. So can somebody tell me what are the values that I should write in the second column?
Okay, okay, okay. So we in that I have 14, then I have double of that, then I have double of that. Okay.
No, no, number of slots I'm asking, not the symbols.
Oh, okay. Uh,
Okay, if you want to add symbols, that also I can do that.
slot is one. Yes, one slot. Yes, one. One slot, then two slot, then we keep on doubling it. Yes,
Basically, it is 2 power mu,
yes, yes.
where mu could be thing. And number of symbols per slot, how many?
14, then 14. Yes, yes.
So
All of
that is
them.
the thing. So because now we can have much smaller and smaller slot length, we can able to easily pack more and more SS burst in time domain as they go to higher numerologies, which we typically use in FR2 frequencies.
Got it, sir. Yeah, got it.
Ah, so I think Ranjita, you are asking something on IMSA and other thing. Yeah.
Sir, actually, we know that IMSI and MSISDN have a 1:1 mapping, and now we have this concept of, it's a generic query, sir. We have this concept of number portability, right? So how are we achieving it? Like in MSISDN, we have this national destination code, which will be specific for the operator, right? So how am I able to go to a different operator and get the same number?
Yeah, I think your question is not what I covered as part of this course. Earlier, I used to have a couple of
I
slides that talking about number portability. What happens is in India, I think if I am not wrong, we have 2 or 3 companies who kind of won the bid when a DOT wanted to implement national number portability scheme. So what happens is these are like a national level. Oh no, not 3. It is only 2. One for North Zone and one for South Zone. And these entities are these organizations are responsible to maintain national level repositories. So what happens is whenever you make the call, first your call goes to this national database. There you maintain the mapping between your number and operator and other things. So accordingly, call will be routed to the respective operators. So what we are
Okay.
doing is we kind of brought in one more gateway using which we are able to map them to the right operator. Even though what you said is correct, the number is still remaining the same, even if you move from one operator to other operator, where you are saying national destination code is uniquely given to different operators. Yes, you are right.
Okay, sir. Thank you.
Okay, let me get started with today's class in that case, not this one. Okay, I think I covered. Okay, so yeah, so high level, this is what happens in the 4-way handshake. First, user equipment will take one of the preamble. And I hope, okay, I didn't, okay, so this is what we discussed in the previous class about taking either short or the long preamble. In the case of short preamble, we have 139 bits, which you can modulate into 139 symbols. And then you can repeat it either 1 time or 2 times or 4 times in the time domain and pack them inside one RACH slot of 1 millisecond. So that's what we are doing in the case of, let's say, numerology 0. I think I made a small mistake in the previous class. So if you look at very carefully, this one, the bottom most row, which is talking about the long preamble format 3, having number of repetitions as 1 earlier, but actually it is 4. So that is the mistake that you see in this table. And another mistake that I made is I had to go back to, yeah. So do you remember this particular page that I was trying to show earlier? So where I was talking about 4
Yes.
different long preamble format. Where in the case of format 0, we have only one code sequence. And in the case of format 2, we are repeating it 2 times. And also we have more guard period. So maybe you can use it when cell range is like a micro cell kind of thing. Then if you have like really a macro cell, then you, and especially when the channel conditions are really bad, then you can think of repeating the code sequence 4 times. So then the mistake that I was trying to tell you is if you look at the code format, sorry, not code format, the preamble format 3. So I was showing you that unlike, like if you try to compare these two, so I think you should be able to see both of them in a single screen now. In the case of format 2, you see it is having a length of 4.3 millisecond and having four code sequences with cyclic prefix and guard period. And when it comes to the format 3, you can see that I have same structure, except that length of each of these things have shrunk significantly in the time domain. I was saying that this is possible because format 3 is meant for short preamble. That is not correct. If you look at the table that you see it here, it says that format is 3 and the length of the random access preamble is 839 bits. That means preamble format 3 is also for long preamble, not for short preamble. And if you look at the subcarrier spacing that is used, unlike the previous one, we have 1.25 kilohertz in frequency domain. Here we have 5 kilohertz. So what you can notice here is in the frequency domain, the width of each symbol is increasing by 4 times. Do you all agree with me? Compared to here, can you try to look at format 3 table and format 2 table and look at the subcarrier spacing. It is 1.25 for format 2 and it is 5 kilohertz for format 3. Basically, it is a multiple of, basically it is multiplied by 4 times. Then you can get this one. And interestingly, if you look at what is the length of a code sequence in the case of format 2, can you look at the picture and tell me what is the code sequence length in time domain? It is all written in the screen. In the
So every code sequence is 0.8006.
no,
And there
look
are
at the picture. Look at the picture. It is already written below the picture.
Oh, 4.3.
No. I'm asking length of a code sequence. I'm not asking the total length of the preamble.
Oh, okay.
So how many code sequences I have here in format 2? In case of format 2, how many code sequences I'm repeating?
There
How
are
many
4 code sequences.
and the length of each of them is,
0.8006 ms.
in other words, 800 microseconds, right?
Yes. Yes, sir.
Okay. So come look at here and see what you observe.
So same 4 code sequences, but the length of each is 0.2 or 200 microseconds.
So what you can say by how do you compare this code sequence with basically how do you compare this format with the above format?
Sir, it is shortened. The code sequence length in time domain has shortened by 4 times.
And increased in frequency domain by,
4 times.
because we are using the subcarrier spacing of 5 kilohertz.
Yes,
That
sir.
means logically they are same. In one case we are playing in time domain and other time we are squeezing in frequency domain.
Yes,
Okay.
sir. Yes.
And I was saying that mistakenly in the previous class, it is meant for short preamble. But what you see beyond like format A1 and other thing that you can see clearly, format is A1, length is 139 bits. And we are talking about using the subcarrier spacing. In this case, I'm talking about most of the cases 2 power 0. Then in this case, it is 15 kilohertz. Then it could be 30, 60, 120, not 120, 240 and other things, where you are repeating it 2 times. So these are for other cases, okay? Now you can see that length are even shorter actually. If you look at in this particular case, format B2, the code sequence length is 66 microsecond. It is much smaller. And this we are using in higher numerologies and especially in FR2 we'll be using it. Now, because each code sequence is taking only short time in time domain, now I can have, like if I go back here, not this one. If I go back here, this is what I was showing you. Now I can have a slot where I can pack here. I'm packing 2 RACH occasion in time domain in a given slot, because each of them is now taking only a part of the slot. So that is the beauty of using short preambles, where I can have more than one RACH occasion in the time domain, where it is possible to have maximum up to 7 in time domain and 8 in frequency domain. So that's what this number 8 is for. How many in frequency domain, and in the time domain, it could be up to 7. Okay, so this is about the guard period, where I was talking about you set the guard period based on the what is the range of the cell. Then you can calculate the propagation delay and you set it as the guard period. Okay, so I think this is what I was showing you, where each user equipment is transmitting preambles in one of the RACH occasions. Then the base station is sending random access response, which contains the preamble ID. Each preamble has an ID that is called rapid random access preamble ID. Let's say if the base station is configured with 64 preambles, so then we can manage this with 6 bits, right? So that is the case. And also it is giving a timing advance and uplink grant for transmitting message 3, and it is ascending a temporary cell radio network identifier, which is of 16-bit length. Then the user equipment is transmitting RRC message, that is a connection setup request, followed by message 4, which is called contention resolution message, along with connection setup, like where the base station is transmitting configuration related to signaling radio bearers and other things. After that, we do the registration, then the data transfer. Okay, so let's look at how these steps are done in a bit more deeper manner. Okay, so I was showing that preamble is important in the sense that unless it synchronizes with the base station in uplink, it cannot send any uplink data in uplink. We use something called Z02 sequence in the case of preamble. Same thing was used even in LT. We have long and short preambles. These are the things I was talking about. In the case of long, we have 4 formats with a different subcarrier spacing and different number of receive blocks in frequency domain. And then we have short preambles, which can be used both in FR1 and FR2, while long preambles are the kind of adoption from LTE. So short preambles are something that have been newly added in NR. Basically, we are kind of reducing the overhead. Why to unnecessarily transmit long preambles and waste the resources? By reducing the preamble length, we can pack more RACH occasions in a time domain and able to reduce the signaling overhead. And as you can see, there are 8 different formats numbered A1, A2, C0, and C1. And also we have combinations like A1, B1, and etc. So lots of things where the base station is advertising which is the preamble configuration that is using as part of the SIB1. So by knowing that, okay, this is the configuration that base station is following, each user equipment can take one of the random access occasion and start transmitting their respective preamble for synchronization in uplink. Now, if you look at in terms of the preamble, each preamble is associated with an ID that I already explained, which is called rapid. And interestingly, each preamble is also associated with something called RARNTI, Random Access Radio Network Identifier. I will come back and explain in the following slide how to calculate RARNTI, where the beauty of this RARNTI is the base station, based on time and frequency resources in which it is receiving this particular preamble, it can calculate or deduce what is RARNTI rather than transmitting this RARNTI explicitly as part of the preamble sequence. Okay, that's what I will discuss in the following slide. But when it comes to the preambles, we can designate certain number of preambles also for contention-free operation, where the base station can say that out of 64, let's say 10 preambles are reserved for handovers. During the handover, what happens is first the base station will assign one of the preamble which is reserved exclusively for the contention-free access to the user who is supposed to do the handover process. Then it will transmit the preamble and it is assigned exclusively to the one user. There is no chance of other users also randomly selecting the same preamble and leading to the collisions. So as you see clearly, the continuous preambles are used in the case of time sensitive scenarios where you don't want to take the risk of the connection getting failed and other cases. And another interesting thing that is also done in the case of preambles is the remaining preamble. Let's say if I say I have 64, out of the 10 are gone as part of the contention free, then I have 54. I can divide this 54 into two groups, group A and group B. And I can say that rather than a given handset randomly selecting one out of the 54 preamble, we can say that handset can choose one out of 27 from one of the group A and group B, depending on how much amount of the data that have to transmit in uplink. The case one is group one, where this kind of preambles are selected by handset to transmit the preamble in uplink when the channel conditions are good, okay, and where it can actually transmit larger packets. The group E is used for an opposite situation when the uplink channel is bad and where it wants to transmit only small data. Then your handset will select one of the 27 preambles from group B. So what happens is when the base station is receiving a preamble, that means when the base station is decoding the preamble, it can know from which of these two groups a given handset has transmitted the preamble. If it comes to know that, okay, this preamble has come from so-and-so user, which belongs to group A, then he can provide larger uplink grant to that particular user because it knows that channel is good and that user is having more data queued in its uplink buffers. In the opposite case, it will allocate only a small uplink grant because channel is bad and even the user also doesn't have so much to transmit an uplink. So that way, rather than giving only a small uplink grant all the time, because base station doesn't know when the user want to transmit anything in uplink, how much is the queue size. That problem is kind of addressed by using these preambles. And we have done one of the work 3-4 years ago. So where we were kind of talking about the case where supporting these machine-to-machine communication, in other words, IoT traffic. So compared to human users, we have so many number of IoT devices connected to the base station in a given region. So what happens is we don't want when you're trying to make a voice call and when an IoT device wants to transmit something in uplink, we don't want your voice call getting contented along with an IoT device transmitting a small data in uplink. So the idea at the time was is use, let's say, group one of the group, let's say group A can be exclusively given to IoT devices and group B is given to human users. So that way, by knowing that, okay, I have received a preamble from group A, the base station can know that, okay, it is coming from an IoT device. Then it can allocate a small grant and also maybe delay in providing the grant to prioritize human users. So all these cases are possible by knowing which preamble a base station is getting. So like that, there are lots of papers in the literature that you can see on how to group the preambles and how to take advantage of the preambles as part of providing the uplink grant to the users. So let me explain about what is RA-RNTA and what is the significance of this. So RA-RNTA, the random access RNTA, is basically telling only one thing. It is helping base station to know in which slot and in which symbol and in which RACH occasion a given preamble is coming to it in uplink. So look at that equation. It has SID. So look at what is SID. It is nothing but which symbol out of 14 symbols in a given slot. So actually it is wrong. it should be okay. Yeah, it is okay. It varies from 0 to 13. So that way 0 less than or equal to SID less than 14 is correct. Yeah. And the second one is the TID. TID basically talking about in which slot you are transmitting. So I hope all of you agree with me that in a given frame, so we have 10 into 2 power mu slots. In the case of numerology 3, so this becomes 80. So that is the case of TID. Okay, then we have FID. So I was mentioning that we can have up to 8 RACH occasions in the frequency domain. So that's why it is varying from 0 to 7. So then whether we are talking about a case where base station to UV communication versus UV to UV communication. So this is what I was talking about in the case of V2X. In the case of V2X, where one vehicle directly communicate with other vehicle using 5G NR-V2X, in that case, this particular flag is set to 1. Otherwise, this flag is set to 0. So that way, these are the things that are used to uniquely identify in which occasion, basically in other words, in which slot out of the 80 slots, and in a given slot, which symbol from which we are getting this particular RACH occasion or the preamble in uplink. And in the frequency domain, if there are more than one, like in this case, K could be up to 8. So which of them is really helping the base station to estimate or not estimate to calculate this array RNTA? Let's look at this figure and help me out to calculate array RNTA. So let's look at the case where in this case I'm having, let's assume that this periodicity is 20 millisecond, and assume that each slot here is of 1 millisecond. And okay, let's take the case where no, okay, I should draw like this. So I have K equal to 2. So that means I have 2 RACH occasions in frequency domain. And or maybe I will make it even simpler, and let's assume that okay, periodicity is 10 millisecond. And if you look at very carefully, so from here to here, I have 10 slots. Okay, and let's assume that in a given slot, all 14 symbols are used for preamble. So this is the example that I wanted to tell you. So in this particular case, so can tell me if one of the user has selected this particular RACH occasion. Can you tell me what could be my RA RNTA if this is my RACH occasion that I have used to transmit my preamble in uplink to the base station? To start with, so can somebody tell me what is my SID?
So SID, it's an index of the first OFDM symbol. So
Right.
if you are using all of them, then it will be 0.
Correct. And TID?
Index of the first slot of the specified path symbols. Frame. Okay.
Look at the illustration and how many slots I have.
You have 10 slots.
And the one that I highlighted is
Okay.
falling into which slot?
Oh, okay, okay. So that is 8, I think.
No,
8.
this is ninth. So
Oh,
zero, we have to start.
okay. Yeah, 9, 8, 7, 7.
So this is 7. And FID, what is my FID?
Uh, FID is 1.
1, because it is 2. So it is 0 here and it is 1 here, right?
Yes, yes.
And I'm talking about communication with the base station. This is 0.
Okay. Oh, 0 for normal uplink carrier and 1 for supplement.
Supplementary uplink carrier, yes.
Okay. Okay, so 0.
I think the supplementary also may mean the case of, I think supplementary link is only for device to device, if I'm not wrong. But anyway, in our case, yeah, it is 0, yes. So that it is like, so 1 plus how much?
178.
Oops, okay. 14 into 7
Oh, 179 then. Sorry, guys.
plus 0, right?
Okay. Oh, okay. No, I did wrong calculation. Okay.
I hope all of you got this point. So if anyone having any doubts about how to calculate RA RNTI, so you let me know.
Okay, 1219.
How much? 1, 2?
1219.
So what happens is when the base station receives a preamble in one such RACH occasion, it knows what is the first symbol and what is the slot, and it also knows what is the RACH occasion in the frequency domain, and also it knows whether there is a uplink or whether it is a supplementary carrier. That way base station can calculate what is the RA RNTI associated with the current uplink preamble reception. Okay, so
But
next, okay, go ahead, Suranjan, yeah.
so this is the temporary RNTI, right?
It is not temporary, it is a random access RNTI. Temporary RNTI is something called TC RNTI.
Okay. So this is the RNTI that is used in subsequent communication.
No, I will come back. Just hold on for that part. So
Okay.
first understand what is how RA RNTI is calculated by the base station.
Okay.
So is this part clear?
Yes.
So one thing, sorry, like it's bit like outside the context, but like this TID is the type ID or like it's something else, like
TID now.
this.
What is TID? Okay, TID is basically, see, if you look at here in a given frame, which slot I'm using for transmitting this preamble. That is what I'm showing it here. In this particular example, my frame containing 10 slots, right?
Yes.
Out of that, this one, the user has transmitted preamble using this particular RACH occasion. This RACH occasion is transmitted in slot number 7.
Okay, fine. Okay, so okay, fine. Because actually, I was asking because while we were working on the NSC project as well, so there the type ID was there, RNTI values and everything. So I
Yes.
was just confusing it, like whether that TID, like does this TID stand for the type ID that is mentioned there?
It is not type ID, it is the slot ID basically. T here stands for slot. And F stands for frequency, and here S stands for the symbol.
Okay, sir. Got it. Like this is basically like relative to like what we are seeing in this RACH resource time block, right? Like
Yes,
this is what.
in this particular RACH occasion. Yes, right.
Okay, sir.
See, any other doubts anyone having on this part? Now I wanted to talk about a case where another user has transmitted uh, in this RACH occasion, the one that I am highlighting now. So what is the change? What will be the RA RNTA in that case?
Uh, 14 into 7 plus 1 only.
1 plus
1 plus 14 into 7.
okay. How much is it?
7, sir, 7.
Oh, okay, and not 17, right? Yeah. How much it is?
99.
Okay, so you got it right. So now, if
9.
there are two users, okay, and one user transmitted in this slot the preamble P1, and other user has transmitted preamble P2 in this slot. So by receiving these two preambles, the base station knows that preamble 1 has 1219 as its associated RARNTI. Preamble 2 has 1998 as its associated RARNTI. Okay, is that clear to you? By knowing in which RACH occasion a given preamble is coming, the base station can calculate what is the corresponding RARNTI, even though the preamble itself is not carrying RARNTI. So let me talk about another case. There is another use.
Sir, can you repeat that? Like, that just, that, like, who is calculating it?
The base station.
Okay, so,
So what
okay.
I'm talking about is this case here. So like okay, just hold on. What I'm talking about is, so I have two users, user 1 and user 2. And user 1 is transmitting preamble P1, user 2 is transmitting preamble P2 using the occasion that whatever that we got. So that is, okay, let's call it as 1. And this has transmitted in the occasion 2. So what happens? Associated with this, we have one RARNTI. And associated with this, we'll have another RARNTI. Is that clear? That's what I was showing it here. For in this example, if you come back, so this is P1 and this is P2. So the P1 has, like if I take this one, the P1 has this equal to 12, 19, and in the case of P2, it is 99. So any doubts on this part? Is that clear to all of you? The user has transmitted and the base station is the one that is calculating. This is what G node B is calculating.
Okay, got it.
Okay, so then let me ask you another question where I have two users, user 1 and user 2. They are transmitting P1, P2, RO1. So when the base station is receiving these preamble 1 and 2 in the same random access occasion, so what is the corresponding RARNTI? So let's take the same example that we have taken earlier. Can somebody look at this very carefully and tell me what is this value and what is this value, assuming that the occasion is this one. Now I am talking about the case where both the users have transmitted in this random access occasion, but with the different preambles.
if they are sending at the same RACH occasion, then the value of RNTI will be same, right?
Do you agree? But you are not telling with confidence.
I am thinking like what can change with changing the preamble,
Nothing will change.
right? And preamble is just the data, right?
Yeah, preamble is the code sequence that you are transmitting. Now this is an interesting case where there are two users who are transmitting different code sequence, but at the same time. This is what we have discussed in the case of CDMA. If you recall, when I was talking about the classical multiplexing schemes, we looked at TDMA, FDMA, and finally we also briefly touched upon CDMA. What is CDMA? If you recall,
Code division multiplexing.
so what is the beauty of CDMA?
We can transmit at the same time but have different orthogonal code sequences to distinguish them.
Same time and also at same.
Frequencies.
Yes. So same time, same frequency, but you are using orthogonal codes. That's exactly is the scenario that I just described. I have two users. They selected two different preambles that you can treat it like two orthogonal code sequences, but they're both transmitting at the same time and at the same frequency. That is nothing but this random access occasion one, and they end up getting base station end up getting same RARNTI for both of them because it is the RACH occasion in which the base station is getting. So it has nothing to do with what preamble that user is transmitting. But associated with the preamble one, I have rapid one. So associated with the preamble two, I have rapid two. So basically the unique identifier for a given preamble, like let's say it could be 1 out of that 64, and this could be 1 out of the 64 that are available. 64 that are available. Got it? So yes, the base station has received in the same RACH occasion, but it has received two different preambles. By decoding the preamble, it will know what is the rapid ID for preamble 1, it knows what is the rapid ID for the preamble 2. But in both the cases, it is getting or deducing it as same RARNTI. And this is a kind of a successful case because even though they both are transmitted in the same RACH occasion, because they are transmitted using different preambles, so there is no collision here. So it is a good case, successful case. So let me show you another scenario. I have user 1, user 2. They are transmitting preamble 1, RO1. How much is my RARNTI in these two cases? Can somebody else other than Suranjan can answer this? Anubhav, can you answer?
Sir, if the conditions are same, it should be 1219, right? In this case
Yeah,
also.
correct. It is 1219. You are right. And can you tell me what will be my the rapid ID here?
Sir, one of those 64 IDs.
Yes, but what I'm saying is because it is the same preamble, the rapid ID is also same.
Yes, sir, they're exactly same. Yes, sir.
That's what I'm saying.
Yes,
Now
sir.
there is a problem now. You can see.
Yes, sir.
Now in this case, what happens is now I have two users who have transmitted exactly the same code sequence, exactly at the same time, and also using the same frequency. Then whatever the condition for CDMA is now no longer satisfied because both the users are not using orthogonal code. So this is the case of collision. Right?
Yes, sir.
This is a collision case. And the fourth case, anyway, it is even a simpler case is user 1 and user 2. They are transmitting using occasion 1, the preamble 1, preamble 2. This is the one. And tell me what is the issue? Do you think any issue there in the above scenario? And other thing that I'm talking about, okay, I didn't complete. So it is P2. So this is one particular scenario. So other scenario is, so P1, P1, so RACH occasion 1, RACH occasion 2.
So in the first case, there won't be any issue.
Like you're saying, first is this one, second is
Yes,
this.
yes. So two different preambles, two different RACH occasion, completely distinguishable. But in the second case, there is ambiguity on the side of the G node B, because G node B will be seeing these two same preambles, and it will not understand which UE sent it.
But yeah, that is, you are right. But if you look at this base station has received in the second scenario on two different RACH occasions.
Right.
So if I have to write here RA RNTI 1 and 2, so are they same or different in the case 1?
Case 1 different, case 2 also different.
Yes. So you can actually assume RA RNTA that you are getting here. That means whatever that you have done here is the same that is applicable here, right?
Yes.
So there is no collision, and there are two different RA RNTA. So these RA RNTA are actually nothing but the kind of temporary identifiers using which the base station will be transmitting the random access response. Okay. So again, I will come back. I'll show you how the message 2 and the following messages are going to be coming later. But I hope this part is clear. This example that I was showing about how we can send different preambles or the same preambles using same RACH occasion or different RACH occasion, and how they are corresponding to same rapid IDs or different rapid IDs, same RARNTAs or different RARNTAs. So this is what I wanted to convey here before going forward. Okay. Okay. So now we coming to the step 2. So that is where the base station is transmitting random access response on the downlink shared channel. So what random access response carries is the rapid IDs. So there are two users who are transmitting different preambles, either using the same RACH occasion or different RACH occasion. The response will contain their respective RACH IDs. So that way they can identify that, okay, whom it is really response is coming for. Okay. And it also contains the for each rapid ID, there is also timing advance. That is, base station is calculating and conveying as part of message 2, so that users can synchronize also in uplink by the end of step 2. So it also carries scheduling grant for transmitting message 3 over uplink shared channel. So that is also conveyed as part of the random access response. And it is also given a temporary identifier, that is the TC RNTI, for further negotiation with the network. Okay, so these are the three main pieces that are being carried inside random access response coming from the base station. So let me go to, I think this one. Yeah, right. So I don't know whether you have looked at this call flow. Did anyone look at this call flow diagram? If not, just look at quickly. I'll quickly run through. First, we have the user equipment transmitting a preamble. Okay. So that's what I was describing also. what is preamble, how to calculate the preamble. All that is being shown here. So after you receive the preamble, what the base station is doing, you look at it. Base station is scheduling message to in downlink, in which radio receiver that base station is going to use to transmit message to is conveyed in PDCCH. That way, all the users, whoever is having or expecting something in downlink, they have to listen to PDCCH and look for their corresponding identifier to know in which radio resources their corresponding data is coming. So in this example, if you look at, let's take the simplest scenario where one user has transmitted a preamble using one of the RACH occasion. So what the base station does, it calculates what is the corresponding array RNTI. It also knows what is the rapid ID associated with the preamble. Then in message in this PDCCH, the base station is transmitting on the scheduling information where it is scrambling the CRC with array RNTI associated with this particular preamble. So that if you transmitted certain preamble, the base station is calculating array RNTI and using array RNTI inside PDCH to inform the user that, okay, I am assigning you so and so resources for your random access response. Then what happens? The user will listen on to that particular radio resources to receive the random access response. Now the base station has transmitted and the UV is receiving. So what random access response contains is one or more PDUs, where inside PDUs we have these random access response. Inside random access response in the context of uplink synchronization, we have the uplink grant. Let's look at what is being carried here. This is the random access response. So if you look at here, if there are 3 preambles that are transmitted using same array RNTI, what is the meaning of 3 preambles having same array RNTI? This is the case where there are 3 users who have selected 3 different preambles by transmitting using the same RACH occasion. In that case, the base station identifies all the 3 users with the same array RNTI, and those 3 users will assume that whatever the message that is scheduled in downlink by conveying that scheduling information in PDCCH is meant for all 3 of them. In this case, all the 3 users will decode this message, basically in this case random access message. Inside they see that there are 3 sub PDUs, where each sub PDU contains the MAC payload for random access response. What is the MAC payload? It is containing the timing advance, uplink grant, and the temporary array RNTI. Okay, and if you look at each subheader, is identified with the 6-bit rapid ID. I was talking about 64 different preambles, so that way you can look at the subheader header and come to know that whether it is your rapid ID or some other preamble's rapid ID. So like that it is being conveyed. So now, yeah, we started with preamble. Yes, base station has calculated the array RNTI and has transmitted random access response. Then the user has received uplink grant and also synchronization information so that he can adjust its clock based on the propagation delay, and I can start transmitting message 3. Here, RRC setup request is nothing but message 3. So RRC setup request contains 2 essential information, and one thing that is there, okay, it is not shown here. So what is carried inside these message 3 are these 2 main parameters. One is the user identity and other one is the establishment class. So the user identity could be a random number, like a 39-bit random number that you can randomly generate, or it could be CRNTI if the user is already have CRNTI assigned as part of the previous RACH process. When the user is moving from, let's say, one base station to other base station and other cases, these things will be still valid. So in any case, a identity is conveyed from the user to the base station, which is not the TCRNTA that base station has transmitted as part of the random access response. Then we have the establishment class, not class, calls. Basically here, user is telling to the base station why he or she is doing the random access process. Is it because it is an emergency call, SOS, or it is a high priority access, or it is a mobile terminated access, or it is a mobile originated signaling, or it could be like a mobile originated voice call. That means, let's say you are making a outgoing voice call. So then the establishment class will be MO-voice call. So like that, you have to tell to the base station why we are doing this random access. It's not just the initial random access. Random access is also used in all these cases when you are getting incoming call, or whether you want to make outgoing call, when you're getting a message or data. In all these cases, you have to do the RACH. And why you are doing the RACH, you have to convey inside message 3. So that is what the RRC setup request. So as a response to message 3, the base station has to transmit message 4. In this case, it is RRC setup, but user has to be informed in which radio resources messages 3 is coming in downlink. That is conveyed again similar to the way message 2 has been scheduled using PDCCH. In this case, this is conveyed not using RARNTA. That's what you are seeing in the case of message 2. In this case, it is conveyed using the CRNTA. CRNTA is the identifier that is it is already known. Okay, or it could be like the unique ID that I was talking about earlier, which is assigned as part of the message 3. So if you are a user, you are transmitting message 3 with certain UA identity, and that is what is kept here as part of the PDCH. That way, each user equipment will listen to PDCH to identify its RNTA. And if it is there, that means that yes, that particular radio resource is what assigned to it in downlink. Then it goes there and start decoding. In this case, that is the message 4, which contains the signaling radio barrier configuration and cell group configuration. We are talking about grouping of the cells and other thing. So after that, yes, the user equipment will be saying that yeah, RRC setup is completed, and now it is doing the registration, where it is kind of want to do authentication with the core network before it can start establishing the PDU session and start transmitting and receiving the data. So that way, this is the entire call flow that is related to the standalone access registration signaling. And I have one more document. So in this case, it is a PDF which is showing the call flow. But if you look at even this particular thing, so this I was showing you earlier, not here, I think, yeah, this is the one. So this is also the same thing. If you recall, it is showing all the way from receiving SS block, SIBs and other SIBs. Then you see message 1, then you see message 2 coming in downlink. Then you see message 3 going in uplink, that is RRC setup request. Then you see message 4 coming in downlink, which is the contention resolution message plus RRC setup. Finally, the user equipment will be transmitting RRC setup complete, then non-access stratum registration request. So then you can see all these different messages that are getting exchanged, where you successfully do the authentication. And if the user authentication is successful, then you established a connection, then you establish a PDU context, PDU session, using which you start transmitting and receive the data. So this is case where you are getting the acknowledgement for successfully establishing a PDU context, not context, PDU session establishment. Okay, so I wanted to open this. If you are not opened this document earlier, so can all of you open this document and just walk through what is being conveyed here. Okay, I'm sharing it here. Please open the document. And you can read yourself because I don't know whether the text is readable because it is coming as a video for you, but you can open. This is the example where the user equipment is in RRC ideal state, and there is some AMF which already has UV context with it, and where the user is currently moving from old AMF to the new AMF. So that is the case, but you can ignore that. You can also treat it more like the initial random access. In that case, also user is doing power on. After that, user is in RRC idle state. So look at what is happening in this case. First, I hope you are able to see my screen. Or are you able to see the PDF yourself? So can somebody confirm me? Then I wanted to quickly walk through these four-way handshake to see how it is being.
So we can open the PDF, but it's very small. The writings.
No, you can zoom in, right? That's what I was
Yes,
saying.
yes,
You
yes.
So maybe I can zoom it here. In that case, you cannot read the corresponding description that is coming on the right hand side. So,
Yes.
but that's okay. Right. So now look at this illustration. And this is the case where we have first user equipment, then we have the G node B. Okay, that is the base station. So look at what is the first thing that he's doing. The message one, that is the preamble that is based on Jadov choose sequence that is being transmitted by the user equipment to the base station. Immediately what user equipment is doing, it is setting a timer to see how long it is going to complete this the initial random access. So the T3000 timer is set. So then you see the message 5 or the step 5, it's not message 5, you can say it is a step 5 or the task 5, where the user equipment is decoding PDCH to check its corresponding array RNTI. So then parallelly, what is happening at the base station is base station has allocated a temporary CRNTI. Then the base station has composed PDCCH with a downlink control information format 1_0, where is sending array RNTI. So here what happens is in the PDCCH, the base station conveys to the user that message 2, I'm going to transmit using this particular frequency domain radio resources, this particular time domain radio resources, and I'm going to use this MCS in downlink. So all that information is conveyed in PDCCH, DCI format 1_0 with array RNTA associated with message 1 transmission in uplink. Then what happens? Now the user knows, okay, at what time domain and where in the frequency domain to look for message 2, and also it knows what MCS to apply, the coding and modulation scheme to decode the message. Now let's say successfully the base station has transmitted and user has received message 2. Message 2 carries all this information. One is the timing advance, the uplink grant. NSA uplink grant, again, it is similar way. You have to provide the radio resources in time and frequency domain. Then it also carries what is the uplink MCS, what is the transmit power control command, the CSA request. So all these are part of the uplink grant. Then it is having temporary CRNTI, which is calculated here in the step 6. So after receiving message 2, the user equipment is calculating a random number between 0 to 2 power 39 minus 1. If it is not already having CRNTI, if it already has certain CRNTI, it will set that to UV identity, and it has to specify why it is establishing or doing this RRC. It could be like a mobile originated voice call, or it could be like an emergency call. So that's what it has composed. The message 3 and the message 3 is transmitted in the uplink grant which was assigned to the user. That way, we can have different users transmitting their resources in uplink by using the corresponding uplink grant in time and frequency domain. After receiving message 3, the base station is again sending PDCCH. Now, unlike in the case of message 2, in that case where we used RARNTI to able to convey something to a specific user based on in which random access occasion that particular preamble has been transmitted for sending message 4. So it is using CRNTI if it is already there at the user, or in the case where the user doesn't have CRNTI, where the user has selected some random number, that random number is the one that is kept here and transmitted in PDCCH. That way, user already has the random number, and by seeing the matching in PDCH, it comes to know that okay, I have assigned some downlink resources for getting my message 4. Now that is what you see happening, where the message 4 is coming. Before sending message 4, already a signaling radio barrier is established at the base station at RRC layer. After receiving message 4, even the user also will establish a signaling barrier so that they can do the registration process. So then finally, it is moving from RRC idle to RRC connected. Once it is moving to RRC connected, we can cancel the timer. So that way in step 15, if you successfully received or moving to RRC connect in a certain time interval, the user equipment is canceling the timer and doing the other process. So again, it is also a very long, I think it is a 7-page document, but yeah, this is all talking about how you do the user authentication and establishing the PDU session. Finally, transmitting the data in downlink and uplink. I think that's what, yeah. Finally, yeah, you can see, yeah, you can see here, 100. The step 100 is about downlink data, yeah. And step 95 is the uplink data. So just look at for a couple of minutes and tell me if you have any queries, especially on the random access procedure. That is the first 4 steps that you see here. Step 1, 2, 3, 4, where you are talking about sending message 1 followed by getting a random access response, then sending RRC setup request followed by RRC setup configuration coming from the base station. And finally, you have the message 5, where it is RRC setup complete along with the registration request coming from the user to the base station and the core network.
Sir, that in the first message from Gnode B, they are also sending RARNTI.
No.
No, CRNTI.
No. There are 2 things here, Suranjan. In preamble, we are not explicitly sending RARNTI. By listening this preamble on particular random access occasion, base station is calculating RARNTI and using that to send step 5 thing.
Okay. So basically, in the time frequency and time domain, where the user has sent its preamble in the same time, in the same.
No, not the time. Yes, you are right. User has transmitted preamble in certain frequency and time domain using some random access occasion, right?
Yes.
Based on that, like for example, that what is that? RARNTI is 99. That's what we calculated, right? One of the example.
Yes.
So let's assume that after receiving preamble, base station has calculated RARNTI as 99. Right? Then what base station is doing is, base station is now transmitting this the PDCCH. Inside what base station is saying that the PDCH is carrying this particular information about in which radio resources message 2 is going to come to you. But PDCH can be used to convey scheduling decision for various different users. How this particular user who has transmitted preamble comes to know that its corresponding scheduling decision is carried inside PDCH. So that is conveyed using that RARNTI equal to 99.
Okay, yeah, got it.
So that way the user will listen to PDCH and check whether its RARNTI is there, because anyway make a note that user already knows its RARNTI, because after all it is the user who has transmitted preamble using certain time and frequency resources. So user knows and base station has calculated after receiving preamble. Then the user is listening to PDCH to check whether its RARNTI is mentioned anywhere in the PDCH. If it is so, then it comes to know that okay, base station is going to respond to me by transmitting message to, but which radio resources are going to be used to transmit message to are conveyed inside PDCH. That is nothing but the time and frequency domain resource assignment along with the corresponding MCS. Okay, so yeah, this is about message 2, and I already covered about message 3, where it includes establishment cause and also the U identity. If already has CRNTI, it uses, otherwise it generates 39-bit random number, or we have something like 5GS TMSI. It could be one of these three that user equipment will transmit. Finally, we have this contention resolution, that is the message 4, which basically helps you to resolve the contention or the collision in case more than one user transmitting using same random access occasion using the same preamble. So this is the summary of what I was talking about, where you can see first you are transmitting preamble, which is associated with some RARNTI, and there are some other information that are associated with that. Then the base station is transmitting the scheduling decision in PDCH by identifying the user with RARNTI. Then the base station is transmitting message to, which carries uplink grant, timing advance, TCRNTI. Then the user is transmitting message 3 with UV identity and establishment class, not class, cause. Okay. Then the base station has to transmit message 4. So in which resources message 4 is going to come is conveyed in PDCH by identifying the user with, it should not be, okay, yeah, it could be used a temporary CRNTI, or it could be also based on the CRNTI if it is already having it. Okay. So finally, you can see that acknowledgement is coming for message 4. Message 4, there is an acknowledgement, whereas there is no acknowledgement for message 2 from the physical layer. As you see, message 2 is coming here. As you see, this is message 2, which is coming at the MAC layer to the user, but there is no acknowledgement because there is a chance that there are two users who transmitted using same random access occasion using same preamble or different preamble, it doesn't matter. As long as there are two users who are transmitting using the same random access occasion, then both of them will end up getting same RARNTI. So then if you are letting the physical layer of the UV transmitting up acknowledgement, then there is a chance that more than one user may respond. So that way there is no ACK or NAC here. But that is there in message 4. And so these are the scenarios that I was describing. Okay. Okay, let's look at the first case. So I wanted to, I think one of you answer these things. So look at the first one. There are two users who are selecting different RACH occasions and selected different preamble sequence. So that, like the example is also shown on the right hand side. So they selected different ROs and they also selected different preambles. So can somebody tell me, is there any collision here?
No, sir.
Because they are selecting different RARNTIs and also they have different rapids. What about the second case where they are selecting different random access occasions, but they selected same preamble?
Sir, no
No,
collision
sir.
in
No, right? Okay, so here also we have different RA RNTs because they're selecting different RACH occasions, but they carry same rapid ID. Because the base station is anyway responding using PDCH, in that case, PDCH now carries RA RNTAs of the both the users inside MAC sub PDUs. The corresponding rapid IDs are carried along with the uplink grant and timing advance information. So that way there is no issue. Look at the third case.
Yes, sir, collision in this one.
What about others? All of you agree with me that there is a collision?
No collision
The the codes are orthogonal, right?
Yeah.
because rapid will be different.
So this is the beauty of that. So if there are 64 users who selected same random access occasion, but they fortunately select 64 different preambles, it is the best possible scenario that you can get. There is no collision, and we are able to manage serving all the users or kind of taking the request from all the users in a single batch occasion, even though it may not be practically possible or it has very, very low probability. But still, there is no collision. And look at the last case.
Yes, sir, collision.
Yeah, so this is what that requires the contention resolution or the collision resolution by sending message 4. Okay. Okay, so okay, so maybe let me explain how the collision is going to happen here. Okay, let me start from here. Oh, no, I think I will use my whiteboard so that I can use different colors as well. Okay. Again, so this is the case where I have UV1. Here I have okay. EV2. Okay. And the first thing that is happening here is okay. Okay, I think this example is this is user 1 or closer near to base station. And this is far away. So now this is a case where both the users are synchronized with the base station in downlink. So they know what is the meaning of various slots. Okay, that's what the kind of thing that they have got it. So this case is what I'm talking about is okay, both of them are synchronized in the downlink. So okay, so exactly at the same time because both of them are synchronized in the downlink. So they're transmitting. So let me use different color. No, I should use the same color because so do you agree with me that the way I'm drawing the time at which the message one is received?
Yes, sir.
So the RACH slot is designed in a way such that even though user 2 is at cell edge and transmitting even though exactly at the same time as user 1, thanks to the guard period, the transmission from user 2 will end up coming within the RACH slot itself. But if you look at in the time domain, it will be something like if this is a RACH slot and one guy's transmission is coming like this, like message 1, and other guys think could be something like this. This is also message 1. So this is my RACH slot. So this is what I was showing you here with a certain difference in the propagation delay. So this example that I want to show here is with preamble 1. So this is also with the preamble 1 and transmitted in RO1. So this is also transmitted in RO1. So because both are transmitted at the same time using the same RACH occasion, so both will end up having same RA-RNTA, even though it is not transmitted, but when the base station is calculating, the RA-RNTA that is calculated for both of them is exactly the same. So do you agree with me or not?
Yes, sir. And it will collide because one is the overlapping, no?
So yeah, so now the interesting thing to note down is, yes, there are two users who are transmitting using the same RACH occasion, and the base station is, we are saying that it is collided. But if you actually look at the message, so do you think that base station can distinguish that there are two users transmitting? Look at here.
Yes, first of all, the collision is not there, but in the middle, that collision started. Also, we don't know what is the guard period. So, if the guard period is significantly larger in time with respect to the message time, then there may not be collision.
So look at this case where there is a line of sight from base station between the base station and user, and also there is some obstacle. So let's take this case where user equipment is transmitting message 1. One case it is coming in line of sight, other case it is bouncing out through obstacles and reaching. Can I say that in the both the cases where I have one user nearby and other user far away, in other case I have one user where I am receiving two copies of the same message 1, the message 1 will be like what I am showing here. If you look at the reception at the base station. Do you agree with me or not? So this is
Okay.
what the multipath reception, where the same signal is coming through multiple routes and end up reaching slightly at different time instances. So that way what I'm trying to say here is, after receiving this particular message 1, which is exactly the same, whether it is being transmitted by one user or two users or 10 users, there is no collision here because base station is getting the same. It is as if the two guys are saying the same message. Even though it appears like collision, there is no collision. But there is a chance that in this example, there are two users who are trying to do the RACH procedure. That base station is not aware as of now. Okay. So now what base station does is, it will calculate RA, RNTI. It is now transmitting So message 2. So what is carried inside message 2? A timing advance, uplink grant, TC, RNTA. Let's call it as 1. Timing grant 1, uplink grant 1. Okay, so everything is 1. Same thing, the same message will receive slightly at a different time. At user 2. Now what is happening here is both the user 1 and user 2 think that the timing advance that is transmitted to the base station is for itself. And they use the uplink grant 1 to transmit their message 3. So now what happens is, okay, now it is the most important part. So now based on the timing advance, they adjust their clock and accordingly they are planning to transmit their uplink grant. Sorry, their message 3, which carries let's say UVID equal to 1, the establishment clause equal to mobile originated voice. And because the other user also has set the timing advance exactly like the user 1, so other user also will transmitting exactly at the same time.
So the two TA will be different or same for message 2?
Same. So we have only one message, right? See, base station is transmitting message 2. It is overheard by user 1 and 2.
Okay. Oh, okay.
Got it? It's not that there are, it is basically overheard. Because it's a broadcast medium, both user 1 and user 2 are receiving message 2 that is transmitted to the base station. Both of them are receiving message 2 because the message 2 is identified with, let's call it as RARNTA1. So this is also identified with RARNTA1. So because message 2 is identified with the same RARNTI, both of them think that message 2 is indeed for itself. Then both of them end up transmitting message 3 exactly at the same time. Because user 2 is at far away distance, message 3 from user 2 will come bit late, and assume that since we are taking a random number out of 39 bits, so it has selected different ID, and establishment class could be same or different. Now look at what happened. This is the most important point that I wanted to highlight. So look at what happened. So there are two users who have transmitted using the same uplink grant by adjusting their clock in uplink, even though the timing advance is valid for one of them. Let's assume that this is valid for only this user. So this is correct and for this user it is incorrect, the timing advance. If we take this particular case, so what happens? Yes, message 3 is coming with one ID and message 3 is coming from other user with a different ID, and both of them are kind of reaching slightly at a different thing. Now there are two things that are possible. One case is both of them are collide, like what you guys were telling earlier. Unlike the previous example where message 1 is exactly the same whether 2 users are transmitting or 10 users are transmitting, whereas message 3 is unique for each user. So that way these are like two different messages which are unfortunately transmitted in the same slot, more like a slotted aloha scenario. So one case is, yes, the base station is unable to decode either of these messages coming from user 1 and 2. In that case, both the users have to repeat the RACH procedure after some backoff. Other successful example could be because the user 1 is very close to the base station and its message 3 is coming a bit earlier compared to other message. Base station may be able to successfully receive message 3 because it is getting better SNR for this particular user compared to cell edge user. In that case, the user 2 has to repeat the RACH process and user 1 end up successfully completing its RACH procedure. In either case, we have this message 4 which is transmitted by the base station. So inside it carries the UE identifier. In this case, because I'm talking about it is 1, so same copies overheard by other user. So it has to restart. And this user, yeah, it will end up transmitting message 5 and continue the process. And this user has to select this thing. So that way, the contention resolution is indeed happening in message 4. Because in the message 4, the base station has transmitted identifier of the user 1, the random identifier of the user 1, not of the user 2. Because what user 2 transmitted, so user 2 transmitted its ID as 2, but the base station as saying that I am replying to user 1. Because there is a mismatch, so the user 2 has failed in completing RACH procedure successfully, it has to restart. So like that, we use message 4 for contention resolution. Okay, so this is the summary of what we have discussed all the way starting from transmitting SS block and getting RACH resources informed as part of SIB1, then followed by message 1, 2, 3, and 4 to successfully establish a radio link, followed by doing the registration. Okay, so these are the high level steps. What we described so far is the step 1 and 2 that you see it here. After step 2, a RSC connection is established. Then user does NAS level authentication, and they also agree upon what is the encryption algorithm and what kind of keys to be using for securely transmitting and receiving the data. Finally, then we have this PDU session establishment. If there are like a dual connected kind of scenario, you can also add secondary cells. Finally, you conclude that registration is complete. Then you can have data exchange in both the directions. So whatever that I was showing in the call flow diagram of 7 page and also that web page is a kind of detailed explanation of what you see it here. So we also have another variant of this thing is called two-step RACH. The beauty of this two-step RACH is which is actually introduced in 5G, whereas the four-step RACH is what is followed in LTE and also available in 5G is message 1 and 3 are sent as message A. in two-step RACH, message 2 and 4 are sent as message B. That way we kind of reducing one round trip time when you are doing the RACH procedure. So it is quite a improvement compared to what is possible with 4-step RACH. Also mentioning about this, where as part of the handovers, we can assign a preamble in advance so that we can make sure that there is no chance of two users selecting same preamble in same RACH occasion and end up having a collision. So this is needed for handover case. So this is an example of how things happen in LTE. But as you look at in this figure, where the user is decoding the physical cell ID, then it is decoding MIB, SIBs. After that, it is doing RACH procedure. Then you can see that data transmission happening and downlink and uplink, where the user is transmitting its CQ information. Then the base station is assigning scheduling decisions and scheduling grants, and they're also exchanging using hybrid ARQ. So only in the case of uplink, we use something called the sounding reference signal in PUCCH. That is, whoever is the user who wanted to transmit an uplink, they are given 1 bit flag in PUCCH. It's more like a hotline. Whenever I want to transmit anything upline, I will use my bit. I'll set my flag to 1 and send it in PUCCH. Then the base station will assign to me some scheduling grant, because base station doesn't know how much I have in my queue to transmit an uplink. Then as a response in PUCCH, the user will be transmitting not only the initial data or the first few bytes of the data along with buffer status information. Then the base station can assign in more resources so that I can transmit my data. So this procedure, what I'm showing it here, only here it differs because in 5G we are using SS block, which is comprising of PSS, triplets, and MIB. And you can see this is the difference compared to 4G and 5G. In the case of 4G, we send first triplets, then we send PSS, and PBCH is sent separately, not as part of SS block. Otherwise, the rest of the steps that you see it here for random access, for downlink and uplink transmissions are same, whether it is a 4G or 5G. Okay, so I'm stopping it here.